Okay, a friend of mine asked me to replicate the Lewin loop, except inside where the magnetic field would be entirely contained within a solid iron core. So I have this beautiful old E-core type transformer. You can actually see that the core is kind of in two halves, and it's actually wound inside the bobbin. It's a sheet. It's laminated steel ribbon that's wound in there. One piece on each side, presumably. Then for my two half turns, I've got a red half turn here, a red half turn here, a 47 ohm resistor, and a 150 ohm resistor. Those aren't exactly Lewin's values, but they're resistances and they're different, so we can still test it. I also have a full turn, a yellow full turn here, which I can test. This transformer is actually wound at about 200 millivolts per turn, which I will demonstrate here, I think. So you can see I have the reference signal. I guess I hooked it up backwards on there. But anyway, the blue is my reference signal, and the yellow is the signal I'm testing. And you can see it's about 202 millivolts for a full turn in the transformer. So let's get started. I'm going to measure the voltage produced and dropped on each element around the loop and see if it all adds up to 0 like Kirchhoff's voltage law says it should. So I'm going to be measuring clockwise. So I'm going to have the black lead there and the red lead to the clockwise. I just have these leads that go into my voltmeter and then tee off to my scope there. So, and what I'm actually going to do here is I'm going to use the voltmeter for the precision reading because it's much more accurate than this cheap 8-bit scope is. But I will use the scope to indicate the sign. And the I'll go ahead and turn on the cursors to type track. Oops. There's type track. Okay, so you can actually read the values on the scope too. So if the viewer would like to go ahead and double check what the scope gives, you can see that it's working there too, but it's not as accurate because it's an 8-bit scope and it's not super accurate. So let's get started. I'm going to set the voltmeter to the 200 millivolt range so we get the maximum resolution of the voltmeter. And one thing you'll notice is sometimes the voltage changes a little because I'm running this on mains, so you know, as the load on the local network, power distribution network changes, the voltage might fluctuate a little, but it looks pretty steady. Okay, so we are measuring the voltage between the points here and here on this bottom half turn on the winding, and we are getting 99.7 volts RMS. Remember, this is reading peak here, so yeah, 1.14. So that's really close to the correct peak. But anyway, the scope rounds to the nearest several millivolts. But we can see that this is a positive voltage here. So I am going to keep track of that, and I'm going to call that 99.7 volts, or millivolts, so 99.7 plus. Now, I'm going to actually measure the voltage on the two red wires first, and then the two resistors, just so that I can keep it in order for my calculation here, because I'm gonna just add it up in there. Alright, so now move it to this red wire. Okay, again, we are measuring clockwise. We have the black lead here. We're going around our loop clockwise. We've got the red lead here. And we are measuring 101.0 millivolts. And the sign of that is positive again. Let me get a good look at that. So we are going to say positive 101 millivolts. 101.0. Okay, now I can sum and subtract the negative voltages that we read across the resistors. So now I'm going to move, come on, nothing quite like running clip leads through the delayed stabilized video of a cell phone camera, right? Okay, now we're measuring clockwise, red to the clockwise. And now we are measuring a negative voltage. Why did that put that up there? That's a cheap scope, what can I say? Minus 68 millivolts. Peak. So here, it looks like we're settled in on minus 48.4, because here's where I'm getting the minus from, and this is some 48.4 volts RMS. So I'm going to call this minus 40, because it's in the minus side here, so 48.4. So we're summing the negatives here. Okay, now I am going to measure the voltage dropped across this resistor. Okay, so we're measuring clockwise, and it's negative. I don't know why the scope keeps jumping up to positive, but you can see that compared to our reference signal at that point in time, our measured signal is negative. Here's the zero line right there. Wonder, yeah, we're near 60 hertz. Anyway, so we're negative, and we are at negative 152.4. So 152.4. Okay, so this is our, this is our positive voltages that we're measuring in the across the red wires, and here is the sum of the voltages dropped, which all appeared in the negative, but I'm adding them here and then subtracting them, and 0.1 millivolts. Kirchhoff's law was perfect within 0.1 millivolts. So as far as percentage of accuracy, we know that the whole loop voltage is of 200 millivolts, so I'm going to divide that by 200 millivolts. Look at that. Our measurements were accurate, or agreed with Kirchhoff's law, to 0.05%. See, that's 0.0005, so if I do times 100, then we get 0.05%, which is very reasonable. So it looks like even when the magnetic field is confined entirely, or for all practical purposes, entirely within a solid magnetic core, that Kirchhoff's law, voltage law, still applies perfectly. And if you take issue with me using an RMS voltmeter, there's two things you can do. You can pause the video and take the RMS voltages and convert them to peak voltages by dividing them by the square root of 2. No, multiplying them by, multiply them by the square root of 2. Or divide them by the sine of 45. I don't care. Or you can take and pause and look at the scope screens and figure out the peak millivolts from there and run it. You will find that based on the scope, the error will be a little bit bigger because the scope just really doesn't measure very accurately. See, you'll notice how this jumps up by, so it's 216. Oh, never mind that. 216. I don't know why it keeps jumping up to that, but anyway, when it's measuring, like, I'm gonna change just to something here. Okay, maybe it'll stay steady. See, it says 144 millivolts. then it goes up to 148. It's jumping by a 4 millivolt increment. .148. Anyway, so that error will add up. Oh, and then there's 140. So sometimes it goes down by, so that's basically 1 bit's difference, probably. And it wanders up or down 1 bit, but that's like 4 millivolts because it's a low resolution scope. Anyway, that's how it works, I guess.